So now, as this is going to be the third seminar this week, but anyway, it's going to be fun to hear something about Ramsey numbers by OpenAI. Hyunwoo voluntarily agreed to give a talk. Thank you. Yeah, please start.
Okay, I also would like to thanks to Sanyo for suggesting to give a talk over the AI that volunteer. And also I also would like to thanks to Tony to choose let's do the number 9 about among the 10 advances in the mathematics taught by OpenAI, which is this problem, the vertical triangle Ramsey number, is a super-exponential which resolves the Erdős longstanding open problem. So let's begin with what is the vertical Ramsey number. Maybe most of them people in here know about what is the Ramsey theory and the Ramsey number. But just for the remaining reminder, I give some formal definition of this number. So formally, I will denote RK3 as the minimum integer n, obviously a positive integer n, such that every arbitrary KH coloring of the complete graph of order large n contains monochromatic triangle. So this is the definition of the Ramsey number, the vertical Ramsey number for the triangle, and it is very well known that this number is finite. So we can say that the Ramsey number is exists. So in most of the examples when the Ramsey number is used in the graph theory, people want to fix the number of the colors and wanted to find the monochromatic cliffs as large as you can possible. So in other words, most of applications they are using this very naive statement, like for every graph, subject to large graph, you can find either large cliff or a large independent set. But in here, the situation is a bit different. In here, you just forbid a very small size of the cliff, but we wanted to find the growth rate of this number when the number of host the colors goes to the infinity. So maybe for some people may wonder that why this number is important, why the growth rate of this vertical dimension number is important. Maybe you don't see why this is important. So I wanted to start with a very interesting, motivating example in the number theory. So let's start with a very easy quiz that maybe everyone knows the answer. So let n be an integer in 3, and if there exists positive triple in n such that x to the n plus y to the n equals g to the n. I think this is very easy because everyone knows the answer, right? So the answer is obviously no.
Obviously.
Yeah, because we know that this is the famous Fermat's last theorem, which is I think the most very well known theorem in the only history of the
It's so easy to do, but you don't have a space here to.
You would provide a proof of it.
But anyway, we know the answer, right? So
I was thinking 0, 1, 1, but anyway,
yeah.
these are the positives. I cannot choose.
Yeah, very interestingly, this problem is related to this vertical Ramsey number. I mean, the variation of this Fermat's last theorem. So, what I mean is, so since this proof of the Fermat's last theorem, except Fermat was rigorously provided just 30 years ago, roughly 30 years ago. So, roughly in the century years ago, this was still remains a very huge open problem in the whole mathematics. So some researchers wanted to consider its variations. So for example, let's consider its finite field the counterpart of this theorem. So what I mean is, let's modify the question like let p be a prime just a prime number, which is some much larger than the exponent n. then maybe we can find the expression like a modular button. And maybe we can ask that if we consider this the modular p version, can we find the integer in this case maybe in FP solution of this equation? And surprisingly, in this case the answer is yes, which is proved by Schur in roughly 100 years ago. And his proof uses these particular length numbers. So for this, let's briefly see how Schur proved this theorem. So by using basic algebra, we know that the finite field of order P is multiplicative group is a cyclic group, isomorphic to cyclic group of the order P minus 1. So which means that there exists a generator G in this multiplicative group such that the unit is exactly G to the 1, G to the 2, to the G to the P minus 1. Now in this setting, now let's define the Schur number that denote the S say R. G is the minimum integer n such that every arbitrary R coloring of the integers 1 up to n contains the monochromatic solution of this equation x plus y equals g. It seems like this definition, if you at first class, you may wonder that whether is this number exists or not. And the Schur's theorem says that x plus y equals g is finite, and also it is bounded over by the particular length number. So how to prove this? So I mean this proof and this theorem is the one of the earliest result in the arithmetic length number, and I think this proof is very nice and very elegant. So I want to briefly introduce how Schur proved this. So now let's consider this arbitrary coloring type, which is the n, which is a function 1 up to n to the colors 1 to the r. And now we wanted to find some auxiliary coloring type prime of the, which is an H coloring of the complete graph of order n by using the R colors such that why are you using the red? Such that this type prime Ij is defined by the type j minus I whenever I is less than z. Then obviously this type prime is well defined, so it means that for every edges assigned to exactly one color along the 1 up to r, and also it only uses the r number of the colors. And now just assume that this large n was the same number as this particular length number of the color number is r. Then by the definition of this length number, there exists a monochromatic triangle under this coloring type prime. So which means that let's say there exists some I, j, k such that this chi prime ij equal chi prime jk is equal to chi prime ik, right? Then again, let's move on to the chi prime to just a pi. Then it means pi j minus I equal pi k minus j equal pi k minus I. One key observation is j minus I plus k minus j is exactly k minus I, which corresponds to the monochromatic solution of x plus y equals j. Right? So we have this point. And then the remaining is very simple. One can pretty easily show that this claim implies this finite field version of the Fermat's last theorem. So how? Now we can write each element, let's say A, in FQ star. Like A is g to the some m times ia plus ja, where n is the exponent at the statement of the Fermat's last theorem, and this ja is the real number and the non-negative integer. The range is to 0 to the n minus 1. So, and since this group is cyclic, so we can write in this form. Now, we wanted to color this A by color JA. And since the total number of the JI is ranging up to 0 to the n minus 1, so we can color all the element FP star to the 0 to the n minus 1, so it is an n colorings. The color is used by n. Then again, if you choose this P large enough compared with n, then by this Schur's plane in here, we can find the monochromatic solution such that x plus y equals g. So it means there exists g to the n times I1 plus some common color C plus g to the n I2 plus C or g to the n I3 plus C. Right? And since again this FP is a field, there exists an inverse element of the g to the c, so we can delete this t, c. Then now take x as a g to the I1, y is the g to the I2, z as a g to the I3. Then there exists the solution x to the n plus y to the n is g to the n congruent to the modulo p. So
non-zero solution.
yeah, non-zero solution. Yeah, thanks. Obviously, non-zero solution. So yeah, this is how Schur proved his very famous theorem. Okay. So now I agree that now I assume that everyone knows how important of this multicolor range number, right? Okay, so so now we all know that now the multicolor range number exists. And by using some simple induction argument, you can easily bound this number by some constant times k factorial. But then one can ask that, then how about the lower bound? The lower bound, there is some easy lower bound which gives an exponential lower bound for this number. But so the state for the R, so state of the art was 380 to the k over 5 minus b over 1.
What?
And obviously, yeah. I mean, the obvious lower bound is roughly the 2 to the k, but they improved this to this number. And but because of these AI, OpenAI stuff, so this state of the art is expired now. Yeah, so anyway, we can observe that there is a gap between the lower bound and upper bound. There is some quite significant gap between this. Because this is roughly the 2 to the big omega of the k. But this factorial is by the Stirling's approximation, it is 2 to the big O of the k log k. So in the exponent there is a gap. This is just a k, and in here it is magnitude is k times log k. So obviously now Erdős appeared because Erdős is always asking a question whether which one is tight. So the conjecture of Erdős says that whether this particular range number is exponential or super-exponential. And he offered some cash for this problem. So this is one of the.
How much?
I couldn't remember correctly, but he offered $250 for determine the implicit constant of this one, and $100 for determine either this one or this one, whether which one is correct. Yeah.
OpenAI is rich, so they
Yeah. So the OpenAI will get $100 because it's not finite. So yeah. So but one may ask that then maybe some mysteriously some kind of the parity argument gives that the middle answer, the third answer. So like when k is an odd, then this one is correct, or k is an even, then this one is correct. But some simple, the recursive lower bound gives that this kind of the happen does not exist. So what I mean is the limit of this number exists. This is exist. And how to prove this limit is exist is, I mean exist means I consider this infinity is also a number. So so how to prove this? So we can show that by using the recursive construction of the lower bound, we can show that this the range number, the particular range number is super-multicolor. That means by the Paquet's lemma in calculus, we can show that this limit exists. And I wanted to explain what is the recursive construction, because I think the proof idea behind of this OpenAI's construction is based on this recursive construction. So what I mean is the proposition, maybe this, if I remember correctly, this was first observed by Pan Chung in some decades ago. What she saw is this number is super-multicolor. So the proof is quite simple. So now let's say we will use a color 1 to k plus L. Now we will copy some complete graph. Each of sides are, this one is RK3 minus 1. And by the definition of this range number, there exists coloring that uses the only colors, uses colors in 1 to the k, such that which does not contain the monochromatic triangle in here. And then once we place this one copy in here, and then we copy this one, this complete graph, how many times we will copy exactly this many. Now we colored in here with vertex clusters, but the remaining coloring is these crossing edges. So the coloring of the coloring structures of these crossing edges is quite simple. For example, now again we know that there exists L coloring of the complete, right, on this order, which does not contain a monochromatic triangle. But in here we will use coloring k plus 1 to the k plus L in here, and now we will consider each vertex, each clusters correspond to a vertex in this coloring, in this complete graph and also the coloring. So for example, if these two vertex clusters correspond to some edge which is colored by some number between here, let's say k plus I, then we will color all of the clustering edges between these two vertex clusters with the same color k plus I, and do this for every pair of the clusters. And then one can easily show that this does not contain a monochromatic triangle, because if the triangle was fully contained in each vertex clusters, then by this construction it doesn't contain a monochromatic triangle. And if some triangle forms like this, then this color is liable in 1 to the k, but this color is liable to k plus 1 to the k plus L, so it cannot be a monochromatic. And if the triangle comes from all these edges comes from the crossing edges, then again this construction says that it cannot be a monochromatic. I mean, I draw a monochromatic yellow triangle, but actually it is not a monochromatic in here. Yeah, so this is the proof of this proposition, right? But this construction is somewhat wasteful, because for me, this coloring is too structured. What I mean is, you can partition the vertex clusters such that all the internal edges only uses the colors between 1 to the k, and all the other part uses some disjoint set of the colors. So this is very highly structured. So in this kind of structuredness, there is some waste to using the colors. I think this was the the first step to come up with this super-exponential construction. And also I want to provide one intuition that why this kind of the coloring cannot give us the super-exponential lower bound. So some few years ago, Fox and Park and Soup show that it's somewhat hard to rigorously state in here, so I will just say very roughly. If this coloring on Kn has bounded VC dimension, then the number of then this together with this bounded VC dimension coloring, then if the number of the vertices is much bigger than the exponential, then you cannot avoid the monochromatic triangle. So it means that if you wanted to construct some super exponential lower bound, then you need to avoid some structured one. It means that you may need to mix some random colorings, right? Yeah. So
There's a question by Olga.
yeah.
I just want to ask, sorry, I don't know. How do you define the DC dimension of the color?
Yeah. So in here, so let's consider the set system, right? So maybe consider some vertex in here, and since this is the edge coloring with some many colors, so some of them are colored by a white, and some of them will colored by a yellow. And you will construct the hyper edges, the set system like this monochromatic neighborhood, and also this yellow neighborhood, and consider all together. And if the whole set system has a bounded width dimension, then you cannot get a super exponential lower bound for this monochromatic triangle limestone. Yeah. So it means we need to avoid this kind of the structureness. So what we want to do is, so here in here, the first very structural part is all of these, for each the clusters, they're using the same set of the colors, and also the crossing edges uses the disjoint colors in the internal one. So we want to mix it. So what we want to do is, now maybe if we consider the K edge colorings of the complete graph, then we wanted to use the induction like this kind of a construction, and also having the same copy in here. But in here, we wanted to give maybe K prime, which is smaller than K prime number of the colorings in here. We wanted to assign K prime colors in here. But in this time, we don't want to assign the same set of palette to each clusters. So we will define some palette set as a K prime set, the size K prime set of the four color sets, and we will assign for each clusters. We will assign one by one, and then we will color this each vertex clusters by using this assigned color palette, simultaneously forbidding the monochromatic triangles. Okay, but the one crucial thing is we need to choose this palette set very carefully. So what I mean is, yeah. So let's say this color assign the colors of this set. Maybe P has a size of the K minus K prime, and just assume that this color assign the palette the K minus Q.
Sorry, P is a set, not a set family?
Yeah, P is a.
Or the yellow thing looked like a subset to me, sorry.
Yeah, I mean P is some subset.
Right.
of the working
I
K,
see, so.
and the size of P is now K minus K prime. So this P indicates the colors that you will not using in this vertex
Is
cluster.
this P same as the yellow P?
No, this is a curly P. So
I see. Okay, yes. Alright.
yeah, and then in here, it's easy to color each vertex clusters, simultaneously forbidding the monochromatic triangle, because just fixing one very nice coloring, and then just assigning each color class to some other color. So recolor some other colors, then the whole structure is same. So you can just copy it, but you can use some different palette, right? Then the thing is, then this strategy is nice, but the problem is, then how do you color these crossing edges in here? So this is the main problem in here. So one strategy is, since this color, this vertex cluster avoided this colors in P, and this vertex cluster avoids the color set in Q. So we wanted to color these crossing edges, maybe originated from P and Q, because otherwise, if you use some colors which is both contained in these two, then there is some high risk to making a monochromatic triangle in here. So it means we wanted to use colors to color these crossing edges between the P and Q. And one may ask it, then what about using just the P intersection of Q? Because if you using P intersection of Q, then obviously in here, these two clusters does not induce the monochromatic triangle. But the real problem comes from this, the whole edges comes from the crossing edges. Then this kind of the things can make a, make a monochromatic triangle. So the next strategy is then consider its symmetric difference. Now why symmetric difference is nice? Because if you fix three sets, this is a P, Q, R, and P, Q, and its intersection with Q, R, is intersection of the R, P is empty. Yeah, I mean, this is easily verified by drawing the Venn diagram. So it means if you using the crossing edges by using the colors, by using the symmetric difference, then this kind of coloring autonomously forbidding this kind of the monochromatic triangles. So it means if you adapt this kind of a color strategy, the only thing that you need to control is this type of a triangle, right? Yeah, good. But in here, if the symmetric difference is too small, then it means the most of the colors in here are repeated. So again, then it may arise some danger of the monochromatic triangle. So maybe we wanted to make sure that the symmetric difference is large. And the key property is we can choose the color palette while maintaining their pairwise symmetric difference is large. It's still possible to choose this color palette is much bigger than this Ramsey number. So it gives this property gives the super-exponential lower bound. So formally, what I want to say is so this calculation is somewhat technical to explain, so I will skip all the numbers and the details. But what I want to do is now we will repeat this kind of the construction, like proceeding the induction. So in the OpenAI paper, they fix some stage parameter H, and they run this kind of recursion at the stage 1 to the H. And let's consider we are at the stage J. In this stage J, we will use color J times T, where T is some constant related to H, depend on H. And at each stage, we will introduce T more colors. So we will choose a color palette J in here, subset here, such that we want to show that for all distinct P and Q in this color palette, we want to make sure that the difference is large. I will skip all the details. So just the intuition, we want to find some big number of the families of PJ which having this kind of the
So
property.
those are subsets of size P, size T, so that any but the pairwise intersection have the same size?
I mean, this is a uniform
Yes.
family.
Yes.
So yeah, their difference should be the same because their intersection is fixed, and P and Q have the same cardinality. Yeah, so these should have the same. And if you choose the parameters very carefully, then you can show that there exists Pj with size at least j to the 1 minus literal 1 to the.
Can I just take the sunflower for this? Like everybody share the same intersection?
Yeah, maybe you can take the sunflower, but if you take the sunflower, then the set system, the size of the whole set system will be very small.
Oh.
But what we need to do is we need to overcome this. So in other words, we need to overcome the exponential lower bound. And in here, by using the classical, the Hamming-Bold packing bound, like Gilbert or some of type argument, then you can show that there exists this color palette with the size at least j to the roughly t. And since if you goes to the h is a very large number, then j varies 1 up to h. So it means that j to the t is somewhat super exponential, which is much better than this just the recursive argument in here. So this argument gives the key. I think this is the key argument in here. Okay, then just assume that we have this, and now we now assign this vertex cluster by using jt to the p in here, jt minus q. Now the remaining thing is we have to color the crossing edges such that we don't want to making a monochromatic triangle in here. So what we really need is we have this kind of a property. So in here we have a u and v and w. If this and this was colored by some color alpha, alpha may be some element in here, maybe in here, then it means this color cannot be colored by alpha. This is what we need to avoid the monochromatic triangle, right? Then it means that we need to store some this kind of the relationship to each vertices. So what I mean is, yeah, there and also there is a very nice graph parameter that that can reflect this kind of the relations, which is the vertex, the coloring, the vertex proper coloring. So for example, what I say is, now consider the colored graph in here. So let's say G alpha is a graph induced by the color alpha in this cluster, and if U and V was assigned to a different the colors in their proper coloring, then it means they cannot be colored by alpha, right? So it means that we have to use the property of this proper coloring, and also we have to store the information of the proper colorings for corresponding this colored graph, and then we have to use it to constructing these cross edge colorings. So to do that, they introduce one more variant in this recursive coloring, such that for each vertex clusters we use the previous coloring, and now what we know is their color graph G1 to the G same as 1T. Each of the graph induced by the color I, their vertex chromatic number is bounded by j plus 1. Because we have to store the information about the vertex proper coloring in each vertices. So if this was unbounded, then it gives some worse bound. So we have to put some more imbalance that this is bounded by some number.
This is at the jth step, right?
Yeah, this is at the jth step.
And G1 up to Gj minus 1t is each cluster.
Yeah.
And we're talking about the number of colors used in GI.
Yeah. And then now let's say this multicoloring, we avoid the color in P, and in here we avoid the color in Q. Then now our strategy is we will use coloring from P, symmetric difference of the P and Q. And since this P and Q comes from the Pj, so their symmetric difference is large. Let's say the difference has size at least S, which is again related to some depend on the number H. Thus we can pick the private plus P1 to the PS, which is in P minus Q, and Q1 to the QS, which is in Q minus P. And in here, in each crossing edges, we will use colors P1 to the PS and Q1 to the QS. Then now what we will do is we will use a very interesting lemma of Malone, then Eliezer, and Sangwan and Tamo on head guessing number of the complete bipartite, right? And this is open as reformulation. Now let H, let S is locally H square, rho square H, and then there exists the two functions f and g, which is a function from the vectors h to the s to again h to the s, such that for all x, y in h to the s, there exists the coordinate b, such that the axis, this coordinate value of x is equal to fy's this coordinate value, or x and y is swapped like this. So I will provide this the proof of this lemma a bit later, and now I will show that I gotta explain that why this lemma could give some color strategy in these color edges. So
this means that you can find two functions. Right?
yeah, two functions. I mean,
So,
if you don't have this kind of things, then it's inherently impossible. Because it means if you only have one function, then consider fy, if f is just an arbitrary function, and you can always find x which avoid all the coordinate values of fy. So we need at least two functions like this.
Why is this related to head guessing? I'm trying to.
I mean, this complete. If you consider the complete bipartite graph in here, then you can consider this h is the number of colors of the head, and each of the vectors in here, each of the members in these two sides, they wearing the head, color 1 to the h, but their point of view is just in here, and in here is just in here. So you can see all the other heads just on your different side.
Okay.
And then before they go into the stage, they will discuss some strategy, such that at least one could guess their head color. And if there exists these two kind of the deterministic function f and g, then this side x and y, they may choose a coloring at the strategy at, and they maybe assign a strategy g, and they once they see this, and they answer their value, and once they answer their value, then because of this property, one of them could guess their head.
Oh, there will be at least one person
Yeah,
guessing
at least
their
one.
own hat color.
Yes.
From the function.
Yeah. So this is very interesting. I mean, how they make a connection with this
Okay.
problem. And then now what we want to do is for each vertex V in here. Now you can see these colors using maybe this color uses the color Q1 to the QS in this side. So for this U, I will construct some column for V such that in the colored graph induced by the color Q1 and see its vertex color, proper color of this V, and this will be 1 up to j plus 1. Let's say it is on say C1, then you will understand the C1 at the first. Yeah, I mean, okay. So now this color does not using the P. This cluster does not using the color Q. So it means that this color, this vertex cluster uses the color Q1 to the QS. They uses the color P1 to the PS, right? And for each color graph, like G, Q, I, its chromatic number is bound by j plus 1 because that was our assumption. Then for each vertex V in here, we will make some column of size S such that this ice entry we will give the how can I say the color of V in this proper coloring G Q I.
So GQI is a subgraph of G.
Yeah,
where
induced by this color QI.
edges are
Colored
colored
by,
by that
yeah.
color, and then you get the proper
Yeah.
some fixed proper coloring of
Yeah,
that
exactly.
particular graph. I see.
And then we will do the same thing for this W in here, but now we will use P1 to the PS here. And now let's show that. And now just fix ordering between P and Q. And now we just assume that there exists function f and g in here. And now assume that this triangle inducing a monochromatic triangle. Just assume, and I will show that this makes a contradiction. So since this triangle containing an edge inside in here, so in main using colors Q1 to the QS because it is a monochromatic, so each crossing edges are using the colors only Q1 to the QS or P1 to the PS. So let's say this color is QI. Okay. Sorry, I did not explain how the strategy of how we will color the
crossing edges.
Yes. Yeah, so because of this, so let's say the vector of V is just like this, and vector of W, this is just like this, and which is corresponding to H to the S in here. And now it means that there exists a D such that this is say FW to the D or W D equal G V D, right? Either this is happen. Now we will choose the smallest index D, which satisfies this. And if this happen, this was happened, then we will assign as a QD. And either this happened, then we will assign PD. Okay.
Oh, I see. So for any pair VW, you look at this function F or G.
Yeah. And then see the smallest index D, which satisfies this conclusion. And if both are simultaneously happen, then we will just choose the first one. Then it is well defined now, right? Then now it's almost complete to finish the proof, because just assume that because otherwise it is asymmetric. So assume that this triangle induces the monochrome the same color. Let's say it is a QI, because each crossing edges should uses only the numbers Q1 to the QS or Q1 to the PS, but they using the internal edge in this cluster. So their color, if they are monochromatic, their color should use 1 over the Q1 to the QS. So let's say this triangle is a monochromatic triangle induced by color Qi. Then it means this coloring property, this is a Qi. It means with ith color is same to the W's in now V and U. Is same to the U's ith color, right? But their color is corresponding Qi, which was forbidden because the definition of the proper color. And if you proceed this 1 up to H, you can get a super exponential roll bound, because this palette number J to the T is super exponential in terms of the T. So this is how they generate the super exponential improvement on this triangulation. So if you choose parameters very carefully, then what you can actually get is RK3 is at least K to the 1 over 3 minus literal 1 to the K. So this is how they prove the neural one. Yeah, so now I want to briefly discuss what can we do further motivated by this kind of the construction. Well, I want to introduce some related problems with this. I mean, I think this lemma, the proof of this lemma, I wanted to explain it, but because of a time limit, I will skip it. But I recommend to the proof of this because it's very, very elegant. So yeah. Okay. So now I briefly wanted to discuss some several possible directions. I mean, obviously, the first direction is just determine this the correct growth length of this vertical length number itself. So what I mean is, so now, as I said, the upper bound is still having the factorial upper bound. So it is still the k to the 1 minus literal 1 k. But this OpenAI's the recent lower bound is k to the 1/3 minus literal 1 to the k. But there's a still gap between its exponent. It is a 1, but it is a 1/3. So I think it is another challenging problem to narrowing the gap between this upper bound and the lower bound. And the second is what about the order cycles? So so far again the state of the expired the state of the art was let's say RK C12 plus 1. So it means it is a k color Ramsey number for order cycle of length 12 plus 1. The roll bound was proved by Day and Johnson several decades ago. This one is Day and Johnson. And the upper bound was quite recently proved by k to the k over l plus liter over k by many people like Aksenovich and Kames van Battenberg and Jenscher, Mitchell, and Bindström. But very recently, Raphael Steiner, I can write the date just 3 days ago. He improved all the Gauss Ramsey, like not just forbidding this long cycle. If you simultaneously forbidding the monochromatic C3, C5 to the C12 plus 1, then this lower bound is again the super exponential, but a bit worse bound. Here the log to the L minus 1k means the iterative logarithm, like log k. But the thing is, this is just the k to the big omega of k. But here is, I mean, I can say that this is the 2 to the big omega of k times log k, but it is 2 to the big omega of k times log k. So again, there's some gap between here. So I think this is also another challenge problem to determine whether this one or this one, which one is more close to upper bound or the lower bound. And also, so another thing is, then what about the sure number? About the some pre-colorings. So sure numbers. So this number are x plus y equal g. So I will remind what is this. So this means that the smallest integer n such that arbitrary r coloring of the 1 to the n contains a monochromatic solution of this equation. And this was bounded by R3K as I demonstrated at the first of my talk. But still, the inverse direction does not know. So for this number, is the state of art is just still exponential. I mean, we cannot use this kind of coloring in here because, as you can see, I erased so you cannot see, but anyway. If you find your memory, the coloring strategy to showing this one is we use the Cayley-like graph, which is highly structured, somewhat highly structured. So we cannot using this kind of coloring. So I think this is again some very interesting challenge problem to finding some super exponential lower bound for this sure number. Also, another thing is then one can ask that then what about the hypergraphs? For example, what about the multicolor range numbers for the tetrahedron or the higher simplicial complexes like K R plus 1, Ramsey, K. So there is a very nice argument of the Erdős and Lado, like stepping up and stepping down argument, such that you can see that the range number of K are for hypergraph with the K plus 1 vertices has a tower type growth, like T to the R equal the K rho K, and it is T to the R equal omega over K.
T means RT.
Yeah, it is a tower function where the T1 x is just an identity function and Ti plus 1 x is 2 to the Ti x. And the upper bound was Erdős, Lado, and Hainar. And this lower bound is done by Aksenovich, Jarfas, and Liu. I mean our Hong Liu, and Dubai. But if you look closer of their proof strategy, you can see that indeed they proved stepping up lemma type theorem. So combining with this recent progress on the super exponential lower bound, and together with their argument, you can replace these two just a big omega over the k log k, which matches the upper bound.
Ah.
So this is I think this is a very nice result. And finally, I want to discuss something about the Shannon capacity.
Do you mean that this replacement is mentioned?
I mean, haven't mentioned they using an induction to proving this rule by itself.
Uh-huh.
But actually, what they did is they did stepping up type things.
I see,
So what I mean is the Ramsey k, r plus 1 is roughly bigger than 2 to the r k,
Uh-huh.
k r minus 1 are this kind of
I
things.
see. So any improvement
Yeah.
on R3K
Yeah,
will
yeah.
imply this.
Yeah.
Then
I mean,
we
we need to choose some careful numbers, but roughly they prove this kind of things.
I see.
And when this k is large enough.
Uh-huh.
Yeah. So and then finally, I wanted to discuss about the Shannon capacity, which is related to this multicolor triangle Ramsey. So maybe some of you don't know about what is the Shannon capacity, so I will start with the definition of what it is. Shannon capacity is one of the most crucial concepts in the information theory. So let's assume we will use only alphabets B, P, D, Q, and G, which looks somewhat similar, right? So when I was a childhood, I always confusing in these 4 characters. So we can indicate which characters are confusing. I think these two are confusing, and I can easily recognize, distinguish these two. And also some of these Q and G is confusing, right?
Okay.
And just assume that maybe in Korea we only have these 5 characters. Then if you want to send some message to your friend by using these 5 characters, then sometimes it may feel confused, right? So you and my friend maybe agree then okay, then let's use some limited families of the code word that avoid the confusions. So to do so, we can send like B, B, D, P, Q, G in here, and also P, G, E, G, P, P. Then according to this confusion graph, you can distinguish these two code words because I mean these pair are confusing, but B and G is not confusing, so we can distinguish these two. Okay. So this is a key concept of the channel capacity and in the information theory. So I wanted to write this kind of a concept more rigorously. So to do so, I'm gonna introduce the strong product of the graph. So let okay, G. One's color is not good. G be a graph, and what I want to do is I want to define the strong product of these two, which says that if the vertex set is forming like U, V, which is the Cartesian product of this VG, and you will adding H, U prime and V prime. If and only if either U and U prime is same or they are adjacent in G, and also simultaneously V and V prime satisfies this property simultaneously. Then you are adding these two edges. And if you can consider this again and again, so if you just assume that we from product of G K times, then we will just abbreviate it as G to the this box to the K. And if you make again some confusion graph of these 5 lengths cold wall in here, and it is correspond to G to the how can I say, G to is something K, right? Then the definition of the maximum family of the cold wall K, the length K, that it does not arise any confusion, is exactly the same as the independence number of the G to the K, right? And the channel capacity is its growth rate. So channel capacity of the graph is its growth rate. Okay. And we will denote it as big, too big, big set of G. So this is the definition of the channel capacity. Right? And why this is related to this hyperbola length, multiple triangle length number? Because okay. I will promise you that I will finish within 5 minutes.
Okay.
So there is a very nice lower bound about this the channel capacity by the independence number. It is pretty easy to prove this nice lower bound, and this is again upper bounded by so-called the Roberts zeta function. I will not give a rigorous definition of what it is. And this is again bounded by the chromatic number of the complement of the graph G. And then, now one can ask that since this channel capacity is lower bounded by its independence number, so maybe if there exists some function such that this channel capacity is upper bounded by some function of this independence number. But OpenAI's proof gives that it is impossible. So what it means is just fix say K coloring, K edge coloring of K, Ramsey K, C minus 1, which does not contain a monochromatic triangle, and just consider its subgraph induced by each color, say G1 to the GK. And then what we will do is, let's say, define G is this graph. So here is just the.
So what is G1 to GK? Is it like?
So this G1 is the graph which induced by the color 1. And G2 is
the same vertex set.
Yeah, on the same vertex set. But in here we will just consider their disjoint copy and then take them as the complement. And this V shape means that they're complete joint. Then you can observe that this alpha G.
Complete joint meaning you put edges complete.
Yeah, like a complete bipartite. It is easy to show that alpha G is a 2 because between two clusters we put the complete edges between the two clusters and we take the complement of triangle free graph. So it means the independence number is just a 2, right? But in here, now what you can see is now you consider the k-fold strong product of this G, then you can see that for each V in this, let's say V KR K3 minus 1 for each V, their diagonal copy V1, V2, UK, and U1, U2 to the UK, and so on. They form an independent set in here because since this was the partition of the complete graph, and it means there exists some edge in here. There exists some edge in here in some color, but we take their complement. It means that in one graph, one is not connected by an edge. So the definition of this the strong product, they cannot form an edge in this graph.
So I'm a bit confused. So you take V1 of the VK and then U1 of the UK. So what are you? So are you taking arbitrary sequence?
No, I mean, so what I mean is, so this G1 to GK was the partition, edge partition of the complete graph, and then we take them as a disjointly, right?
Oh, so VI's are copies of V.
Yeah, right, exactly.
I see. And UI's are copies of U.
Yeah.
Okay.
Then, since this was from the edge partition of the complete graph, there exists some coordinates such that they was connected in some of the graph, but we take the complement. It means that they was not connected in here. So the definition of this strong product, they cannot be joined by an edge. So they forming a independent set, which is super exponential because V was the super exponential. So by normalizing it, this Shannon capacity of G cannot be bounded by any constant. Yeah, it is
Any
some
constant multiple or
any some universal constant, some absolute constant. I mean, for any given absolute constant C, you can always find the large enough K such that there is the Shannon capacity of the corresponding graph G is bigger than the K, bigger than the C. So this is just the calculation.
Right, calculate.
Yeah, so I mean, yeah. So yeah, I'll skip the calculation.
Oh, I see. So, but just conclusions.
Yeah, so the conclusion was if this graph, there exists a G where its independence number is 2 and n of n vertex, it is n raised log n to the 1/3 minus little 1. So it is bigger than any absolute constant if you choose n large enough. So it means that the Shannon capacity cannot be bounded over by any function of this independence number. Then one can ask that, then what about the upper bound of this? So the upper bound of this Shannon capacity, where the independence number is 2, the only known, as far as I know, the only known upper bound was the big of the n1/3, proved by Alon and Kahel by proving the upper bound of the robust theta function. And so my question is, again, I think it is very interesting that whether there exists some graph G which has an independence number is 2, such that their Shannon capacity is bigger than some polynomial like n to the c, that kind of things. Because our lower bound is just a polylogarithmic, but the upper bound is the n to the 1/3. And lastly, I want to say that the the robust zeta approach is not possible to give any improvement on this problem because it was again prove that there exists this kind of a graph G such that the logos theta function is at least n to the 1/3 again by the construction of log alpha. So maybe we need to find some new idea to narrowing down the gap between this polynomial upper bound and polylogarithmic lower bound. Okay, so this was what I wanted to say today, and thanks for listening.
Thank you. Any questions? Yeah.
So for constructing lower bound of quantitative Ramsey number, what I was surprised was there was no like randomness except for the part of head guessing lemma function. So if it is constructive, every part are constructive. So is there a hidden randomness in that head guessing lemma or?
Yeah, in head guessing lemma they use some random metrics. They use
I see.
randomness very heavily.
I see. That's where.
Yeah.
Okay.
And also, except the parts, every part are the constructives, which means that it's highly structured.
So it is not highly structured.
Really?
Yeah.
Okay.
I mean, it is highly structured, then again by the bounded width and the dimension. That in terms of the bounded width dimension, then it cannot give the super-exponential lower bound.
Are these consequences of Shannon capacity also observed by OpenAI's?
Yeah, yes, this was also by OpenAI, but this lower bound, the quantitative lower bound was calculated by me. But if I put this to ChatGPT, then they can also find this one very quickly.
Any other questions? So, let's thank the